We are about to take a deep dive into the treacherous brambly swamp of philosophical logic and the philosophy of logic, with the heroic aim of acquiring true classical, foundational principles of reasoning. What we knew all along, rigorously articulated and defended from the attacks of the critics. Okay, so logic, as I shall describe it, is a field of study where the primary topic is valid rules of logical inference. Let's unpack that. A rule of logical inference, or a rule of inference, is a rule which states that in any conversational context where a set of statements with given forms, premises, are warranted assertable, another statement, the conclusion, is warranted assertable. This is my definition. Although I don't claim it's original, anyway, I'll give some examples of rules of inference for statements in the language of first-order logic. A and B entails A. A and B entails B. A comma B entails A and B. A entails A or B. B entails A or B. If A then B, comma A, entails B. The statement of each of these rules consists of a sequence of statement forms, the word entails, and a single statement form at the end. By a statement form, I mean a first-order logic statement with metavariables, A and B in these examples, holding the place of some parts of the statement. Rules of logical inference can be thought of as descriptive rules, by taking them to describe regularities in people's standards of warranted assertability. For example, in just about any conversational context, for just about any statements A and B, just about any speaker who considers A and B warranted assertable in that context will also consider A warranted assertable in that context. This is one way of interpreting the meaning of the rule of inference A and B entails A. Rules of logical inference can also be thought of as prescriptive rules by taking them as defining norms of assertion. For example, the rule of inference A and B entails A can be taken to be the normative rule that in any context, for any statements A and B which are interpretable in that context, if a speaker considers A and B to be warranted assertable in that context, then they should also consider A to be warranted assertable in that context. So in this section, I'm basically asking the following questions. In general, what rules of logical inference are correct as descriptive rules? And what rules of logical inference should we accept as prescriptive rules? These two questions are closely related. I want to figure out what level of consensus exists around each proposed rule of logical inference, which tells us how correct it is as a descriptive rule. This then becomes the primary consideration in deciding what rules of inference to accept as prescriptive rules. Rules of logic are about as close as we can get to universal rules for debate. For all that philosophers disagree about almost everything, there is virtually no disagreement that in any or just about any context where a statement of the form A and B is warranted assertable, the statement A is also warranted assertable. This is a very simple and self-evident rule, which might not appear to be good for much, and in itself it isn't good for much. The beauty of logic is that by chaining together long sequences of applications of simple self-evident rules like this one can bring one's listeners along on a journey to a final conclusion that may be very surprising to them, that probably they would not have accepted if they hadn't been presented with such a compelling sequence of logical inferences. Logic ends up being one of the great sources of common ground in debates. Rules of logical inference can also be called argument forms. The term argument form is somewhat more neutral in that rule of inference may carry the connotation correct rule of inference to many listeners, whereas the term argument form more explicitly encompasses incorrect rules of inference as well as correct ones. Again, though, both terms literally mean the same thing as I'm using them. Okay, so a case of an argument form is an argument resulting from substituting concrete expressions for the metavariables in the argument form. For example, in the argument form A and B entails A, the spaces held by metavariables are the spaces held by A and B. Here are some cases of this argument form. Spot is a dog and Spot runs entails Spot is a dog. Barack Obama is POTUS and POTUS is male entails Barack Obama is POTUS. Here are some non-examples of cases of this argument form. Spot is a dog and Spot runs entails Spot runs. Barack Obama is POTUS and POTUS is male entails the sky is blue. I will call an argument form valid for a given person if and only if there are no counterexamples to the rule for that person. A counterexample to an argument form for a given person is a hypothetical or real truth-seeking debate context and a case of the argument form, where they consider the premises warranted assertable and don't consider the conclusion warranted assertable. I will only consider a counterexample to an argument form to be genuine if even after participating in thorough discussion and evidencing a good understanding of the relevant issues, the person with the counterexample still finds the premises warranted assertable and the conclusion not warranted assertable. When an argument form is valid for people in general, I will call it simply valid. A and B entails A is an example of a valid argument form. We can also call it a valid rule of logical inference, since every argument form is a rule of logical inference, and vice versa. I am now in a position to articulate the main question about logic in this section. What rules of logical inference are valid? So what language we choose for the investigation is not an entirely neutral choice. When we give formal definitions of rules of inference for a formal language, the syntax of the language imposes constraints on the rules we can straightforwardly formulate. For example, in second-order logic, we can easily express rules of inference that have no straightforward expression in first-order logic. The syntax of first-order logic is specially chosen to make standard rules of logical inference easily expressible. First-order logic is as complex as necessary to define enough rules of logical inference to do all of math, but not more complex than necessary to accomplish this. We can feel good about this choice of language for investigating rules of logical inference. So there is a standard, widely accepted answer to the question of what rules of logical inference are valid for first-order logic. This answer is a set of rules called classical first-order logic, or classical logic, as I shall abbreviate it. There is controversy among academic logicians about whether all the rules of classical logic are valid. Few logicians think there are any valid rules of inference for first-order logic that are not part of classical logic. A greater number of logicians think that not all rules of classical logic are valid. It should be noted that the logicians in this debate employ various definitions of valid, which may not always coincide. Okay. So we will start our way into the central debate in the study of logic by looking at the rules of classical logic. There are infinitely many rules of inference or argument forms that are valid according to classical logic. In order to describe the rules of classical logic in a finite amount of space, we need to use abstraction. The way the rules of classical logic are conventionally presented is by giving a finite number of rules which allow all of the valid rules of inference or argument forms to be generated. There are a variety of ways of doing this, e.g., via natural deduction systems, via Hilbert systems, or via sequent calculi. Here, I will do an informal presentation of a sequent calculus formulation of the rules of classical first-order logic. And this audio format will somewhat impede the clarity and completeness of the presentation, as in the section on statements. Okay, so my presentation is most closely based on the style of presentation of first-order logic articulated in Dave Ripley's graduate philosophical logic course taught in spring 2014 at the University of Connecticut. Credit for the original conception of the rules of classical first-order logic is best claimed by Gottlob Frege and Giuseppe Peano, as far as I'm aware. I don't know if I got Peano's name pronounced right. Hopefully I did. Okay, this presentation requires a concept that is new for this text, the concept of multiple conclusion sequence. A sequent is basically an entailment between first-order logic statements. PA and PB entails PA is an example of a sequent. A multiple conclusion sequent is a sequent which might have multiple conclusions. PA or PB entails PA, PB is an example of a multiple conclusion sequent. In general, a multiple conclusion sequent has the form A1 through AN entails B1 through BM. The notation A1 through AN stands for any finite sequence of statements. N is supposed to be a variable standing for a number. N could be 0, in which case this denotes an empty sequence of statements. N could also be 1, or any higher number. B1 through Bm is another instance of the same notation. Of course, the sequences A1 through AN and B1 through Bm may be of different length. A multiple conclusion sequent has 0 or more premises and 0 or more conclusions. So this presentation of classical logic is based on multiple conclusion sequence. So henceforth, sequent is short for multiple conclusion sequent. A sequent A1 through AN entails B1 through Bm should be interpreted for our purposes as stating that it is incoherent to assert all of A1 through AN and to deny all of B1 through Bm at the same time. If what the sequent states is true according to classical logic, I say that the sequent is valid according to classical logic, or simply valid when context makes the meaning clear. So the sequent PA and PB entails PA is an example of a valid sequent. It states that it is incoherent to assert PA and PB while denying PA. The sequent PA or PB entails PA, PB is also valid. It states that it is incoherent to assert PA or PB while denying both PA and PB. So according to Dave Ripley in Communication with Me, this interpretation of the meaning of multiple conclusion sequence was anticipated in John McFarlane's unpublished but widely distributed In What Sense, If Any, is Logic Normative for Thought, and the notion first appears in the published literature in Greg Restall's 2005 Multiple Conclusions. The interpretation was taught to me by Dave Ripley in his 2014 logic course. I have finished introducing the notion of multiple conclusion sequence, so let us proceed to the rules of classical logic. The rules of classical logic are the rules that state what sequence are valid according to classical logic. A sequence is valid according to classical logic if and only if it can be deduced according to these rules. Okay, so first rule, rule of non-contradiction, rule 0. This rule states that any statement entails itself. For any statement A entails A is a valid sequent. This sequent states that it is incoherent to assert A and deny A at the same time. Okay, conjunction rules. The following rules in classical logic are related to conjunction, i.e. and. 1. Assertion strengthening. Suppose A1 through AN, comma B entails C1 through CM is a valid sequent. Then A1 through AN, comma B and D entails C1 through CM is a valid sequent. What changes between the supposed sequent and the then sequent is that B is replaced with B and D. In other words, given an incoherent set of assertions and denials, including the assertion of B, strengthening B to B and D gives you another incoherent set of assertions and denials. In a second version of this rule, which is also a rule of classical logic, B and D is replaced with D and B. A shorter and less complete way of stating the rule of assertion strengthening is to say that if it's incoherent to assert B, then it's incoherent to assert B and D, or to assert D and B. Okay, 2. Denial weakening. Suppose A1 through AN entails B, C1 through CM is a valid sequent, and D1 through DK entails E, F1 through FJ is a valid sequent. Then A1 through AN, D1 through DK entails B and E, C1 through CM, F1 through FJ is a valid sequent. So in the suppose, we are given two incoherent sets of assertions and denials, the first containing a denial of B, and the second containing a denial of E. The rule tells us that it is incoherent to assert the union of these two sets of assertions and denials, with the denials of B and E replaced with the denial of the conjunction B and E. Denying the conjunction of B and E is weaker than denying each of B and E individually, because to deny the conjunction B and E is to deny that B and E are both true, which is equivalent in classical logic to asserting that at least one of B or E is false. It is also true that simply taking the union of these two incoherent sets of assertions and denials would give us another incoherent set, because adding anything at all to an incoherent set gives you another incoherent set. What the rule of denial weakening tells us is that it is still incoherent, given the setup of the suppose, to combine the two sets and replace the separate denials of B and E with the weaker denial of just the conjunction B and E. A shorter and less complete way of stating the rule of denial weakening is to say that if it's incoherent to deny B and it's incoherent to deny E, then it's incoherent to deny B and E. Okay, disjunction rules. The following rules of classical logic are related to disjunction, i.e., or. 3. Denial strengthening. Suppose A1 through AN entails B, C1 through CM is a valid sequent. Then A1 through AN entails B or D, C1 through CM is a valid sequent. What changes between the supposed sequent and the then sequent is that B is replaced with B or D. In other words, given an incoherent set of assertions and denials, including the denial of B, strengthening the denial of B to the denial of B or D gives you another incoherent set of assertions and denials. Denying B or D is equivalent in classical logic to asserting that B and D are both false, which is why it's stronger than denying just B. In a second version of this rule, which is also a rule of classical logic, B or D is replaced with D or B. A shorter and less complete way of stating the rule of denial strengthening is to say that if it's incoherent to deny B, then it's incoherent to deny B or D, or to deny D or B. Okay, 4. Assertion weakening. Suppose A1 through AN, B entails C1 through CM is a valid sequent, and D1 through DK, comma, E entails f1 through fj is a valid sequent. Then, a1 through an, comma, d1 through dk, comma, b or e entails c1 through cm, comma, f1 through fj is a valid sequent. In the suppose, we are given two incoherent sets of assertions and denials, the first containing an assertion of b, and the second containing an assertion of e. The rule tells us that it is incoherent to assert the union of these two sets of assertions and denials, with the separate assertions of b and e replaced with the mere assertion of the disjunction b or e. It is also true that simply taking the union of these two incoherent sets of assertions and denials would give us another incoherent set, because adding anything at all to an incoherent set gives you another incoherent set. What the rule of assertion weakening tells us is that it is still incoherent, given the setup of the suppose, to combine the two sets and replace the separate assertions of b and e with the weaker assertion of just b or e. A shorter and less complete way of stating the rule of assertion weakening is to say, if it's incoherent to assert b and it's incoherent to assert e, then it's incoherent to assert b or e. Okay, so the following rules in classical logic are related to the conditional, that is, to if-then. 5. Conditional denial. Suppose a1 through an, comma b, entails c, comma d1 through dm, is a valid sequent. Then, a1 through an entails if b then c, comma, d1 through dm, is a valid sequent. In this rule, the premise or assertion b of the sequent is moved to the conclusion or denial side as the premise of the conditional if b then c. A shorter and less complete way of stating the rule of conditional denial is to say that if it's incoherent to assert b and deny c, then it's incoherent to deny if b then c. 6. Conditional assertion. Suppose a1 through an entails b, comma, c1 through cm is a valid sequent, and d1 through dk, comma, e entails f1 through fj is a valid sequent. Then a1 through an, comma, d1 through dk, comma, if b then e entails c1 through cm, comma, f1 through fj is a valid sequent. A shorter and less complete way of stating the rule of conditional assertion is to say that if it's incoherent to assert e and deny b, then it's incoherent to assert if b then e. So this is perhaps one of the less intuitive rules of this presentation of classical logic, and I will have more to say about it later. Negation rules. The following rules in classical logic are related to negation, i.e. not. 7. Negation assertion. Suppose a1 through an entails b, comma, c1 through cm is a valid sequent. Then a1 through an, comma, not b entails c1 through cm is a valid sequent. In this rule, the denial of b is transformed to an assertion of not b. A shorter and less complete way of stating the rule of negation assertion is to say that if it's incoherent to deny b, then it's incoherent to assert not b. So rule 8, negation denial. Suppose a1 through an, comma, b entails c1 through cm is a valid sequent. Then a1 through an entails not b, comma, c1 through cm is a valid sequent. In this rule, the assertion of b is transformed to a denial of not b. A shorter and less complete way of stating the rule of negation denial is to say that if it's incoherent to assert b, then it's incoherent to deny not b. Universal quantifier rules. The following rules in classical logic are related to the universal quantifier, i.e., for all. Stating these rules requires introducing a new notation. For any statement A, any variable name x, and any object term t, let A with x to t denote the statement resulting from replacing all instances of x in A with t. So again, that notation is A with x to t. All right. So rule 9, counterexample. Suppose a1 through an, comma, b with x to t entails c1 through cn is a valid sequent. Then a1 through an, comma, for all x, b entails c1 through cn is a valid sequent. The rule of counterexample states that if it is incoherent to assert b for one specific possible value of x, denoted by t, then it is incoherent to assert the universal generalization for all x, b. In short, it is incoherent to assert any universal generalization that has a counterexample. Okay, 10. Universal generalization. Suppose a1 through an entails b with x to y, comma, c1 through cn is a valid sequent, and that y does not occur as a free variable in any of the statements a1 through an, comma, c1 through cn. Then a1 through an entails for all x, b, comma, c1 through cn is a valid sequent. The assumption that y does not occur as a free variable in any of the side premises a1 through an, comma, c1 through cn is a way of capturing the idea that y is a variable that could potentially refer to any object. The rule of universal generalization states in essence that if it is incoherent to deny b for an arbitrary object, then it is incoherent to deny for all x b. Okay, existential quantifier rules. The following rules in classical logic are related to the existential quantifier, i.e. for some. 11. Non-existence generalization. Suppose a1 through an, comma, b with x to y entails c1 through cm is a valid sequent, and that y does not occur as a free variable in any of the statements a1 through an, comma, c1 through cm. Then a1 through an, comma, for some x b entails c1 through cn is a valid sequent. So the assumption that f does not occur as a free variable in any of the side premises a1 through an, comma, c1 through cm is a way of capturing the idea that y is a variable that could potentially refer to any object. The rule of non-existence generalization states in essence that if it is incoherent to assert b for an arbitrary object, then it is incoherent to assert, for some x, b. Okay, rule 12, the rule of example. Suppose a1 through an entails b with x to c, comma, c1 through cm is a valid sequent. Then a1 through an entails, for some x b, comma, c1 through cm is a valid sequent. The rule of example states in essence that if it is incoherent to deny b for some specific object, then it is incoherent to deny, for some x, b. Okay, structural rules. The structural rules in classical logic are rules of inference that tell us that manipulating the structure of valid sequence in certain ways always yields other valid sequence. In summary, these rules tell us two things. First, that we can add premises and conclusions to a valid sequent to get another valid sequent. This is because adding more assertions or denials to an incoherent set of assertions or denials will never make it coherent. Second, that order and repetition of the assertions and denials does not matter for coherence. So that's what the structural rules tell us. And the following are the structural rules for classical logic. 13. Strengthening. Suppose a1 through an entails c1 through cm is a valid sequent. Then, for any statement b, a1 through an, comma, b entails c1 through cm is a valid sequent, and A1 through AN entails B, comma, C1 through CM is a valid sequent. So the rule of strength, what we've done is just add a B on either side, and B is unrelated to what was there before. So the rule of strengthening states in essence that if your position is incoherent, then your position is still incoherent if you strengthen it by asserting B or by denying B. This rule is called weakening in most other presentations of classical logic. Okay, 14, assertion contraction. Suppose A1 through AN, comma B, comma B, entails C1 through CM is a valid sequent. Then A1 through AN, comma B, entails C1 through CM is a valid sequent. The rule of assertion contraction states in essence that if a position is incoherent and asserts B more than one time, then it is still incoherent if it asserts B one less time. Okay, denial contraction. Same thing on the other side. So from the rules of strengthening, assertion contraction, and denial contraction, it follows that the number of times you assert or deny a statement does not matter for the coherence of your position. To arrive at this conclusion, one also needs to use the rules of assertion permutation and denial permutation. Okay, assertion permutation. Suppose A1 through AN, comma B, comma C, comma D1 through DM entails E1 through EK is a valid sequent. Then A1 through AN, comma C, comma B, comma D1 through DM entails E1 through EK. So what changes between the supposed sequent and the then sequent is that the order of B, comma C is swapped to produce C, comma B. The rule of assertion permutation states in essence that if a position is incoherent, then it's still incoherent after swapping the order of two assertions. Okay, 14, denial permutation. Suppose A1 through AN entails B1 through BM, comma C, comma D, comma E1 through EK is a valid sequent. Then A1 through AN entails B1 through BM, comma D, comma C, comma E1 through EK is a valid sequent. What changes between the supposed sequent and the then sequent is that the order of C, comma D is swapped to produce D, comma C. The rule of denial permutation states in essence that if a position is incoherent, then it's still incoherent after swapping the order of two denials. From the rules of assertion permutation and denial permutation, it follows in generality that the order of assertions and denials does not matter for coherence. From all the structural rules together, it follows in generality that the order and repetition of assertions and denials do not matter for coherence. The final structural rule in this presentation is the rule of cut. This rule is redundant. Genson's cut elimination theorem shows that any sequent that is valid in classical logic can be shown to be valid using just the 14 rules we have listed so far, without using Rule 15, the cut rule. However, sequent derivations not using the cut rule will tend to be much longer than derivations using the cut rule. So here's Rule 15, cut. Suppose that A1 through AN entails B1 through BM, comma C is a valid sequent, and that C, comma D1 through DK entails E1 through EK is a valid sequent. Then A1 through AN, comma D1 through DK entails B1 through BM, comma E1 through EK is a valid sequent. The cut rule is so named because the rule lets us combine two valid sequents, one with C in the conclusions and one with C in the premises, while cutting C out of the picture. The rule of cut states in essence that if it's incoherent for you to assert C and it's incoherent for you to deny C, then your position is incoherent. Okay, so that completes my presentation of the rules of classical first-order logic. For another presentation which is more compact and easier to survey, see Wikipedia's presentation of the LK sequent calculus. Now perhaps this presentation would be easier to survey if it were less compact, or easier to understand. I am quite interested in your feedback on how this material should be presented. I think it could use some examples though, but I don't know. All right, as I have stated before, it is a matter of controversy among logicians whether all the rules of classical logic are correct in all contexts. So before surveying that very intricate debate, though, I would like to explain how the rules I've just laid out can be used. Each of these rules states a very basic principle about what kinds of sets of assertions and denials are incoherent. Most of them are so obvious as to appear trivial, perhaps trivial to the extent of near pointlessness. The reason that rules of logic are useful and allow us to arrive at surprising non-obvious conclusions is that this can be accomplished by chaining together long sequences of applications of rules of logic. The most impressive example of the usefulness of logic is in math. Every mathematical statement that is true according to the consensus of math can be arrived at by applying the rules of first-order logic I have presented to derive progressively more conclusions from a basic set of axioms, or a set of, such as the widely accepted axioms of Zermelo-Fraenkel set theory. So higher mathematicians build ever more complex towers of thought, exploring an infinite space of true mathematical thoughts. This exploration can be continued indefinitely without ever needing to assume more axioms. Logic is also indispensable in philosophy, and in any area of serious truth-seeking human thought. The rules of logic are the most reliable, generally accepted principles of reasoning that humans have. The reason rules of logic are useful is that they can be chained together to form interesting arguments. Let's examine how this is done in the case of classical first-order logic as I have presented it. Consider the following classic argument. Socrates is a man, and all men are mortal. Therefore, Socrates is mortal. We can symbolize this argument as a sequent as follows. Socrates is a man, comma, for all x, if x is a man, then x is mortal. Entails, Socrates is mortal. This is a valid sequent/argument. Let's see how we can prove its validity according to the rules of classical logic. 1. The rule of non-contradiction implies that this is a valid sequent. Socrates is a man entails Socrates is a man. 2. The rule of non-contradiction implies that this is a valid sequent. Socrates is mortal entails Socrates is mortal. 3. The rule of conditional assertion and steps 1 and 2 imply that this is a valid sequent. Socrates is a man, comma, if Socrates is a man, then Socrates is mortal, entails Socrates is mortal. 4. The rule of counterexample and step 3 imply that this is a valid sequent. Socrates is a man, comma, for all x, if x is a man, then x is mortal, entails Socrates is mortal. I will explain the thought process that I used to arrive at this proof, and unpack why the proof is correct. In this presentation of classical logic, every proof that a sequent is valid formally needs to start by invoking the rule of non-contradiction. Recall that the rule of non-contradiction is the rule that for all statements A, the sequent A entails A is valid, or in other words, it is incoherent to assert and deny a statement at the same time. The rule of non-contradiction is the only rule we have which allows one to conclude that a sequent is valid without having previously concluded that some other sequent is valid. Except for the rule of non-contradiction, all of the rules we have are of the form, if one or more sequents of a given form are valid, then one or more related sequents of a different form are valid. To use the other rules besides non-contradiction, one must have some sequence that are valid already at hand. Originally, they always come from the rule of non-contradiction. These considerations told me that for sure, my proof was going to start with an invocation of the rule of non-contradiction. A useful technique for constructing proofs that sequence are valid is to try to work backwards from the desired conclusion to the beginning of the proof. In this case, the desired conclusion is that Socrates is a man, comma, for all x, if x is a man, then x is mortal, entails Socrates is mortal, is a valid sequent. So the conclusion sequent that we're looking to derive is rather long, and it contains details that are not necessary for the task at hand. So we can simplify this sequent and make it easier to work with by replacing the English phrases with symbols. So I will symbolize the predicate is a man by the letter P. I will symbolize the predicate is mortal by the letter Q. I will symbolize the object term Socrates by the letter A. So then the desired conclusion becomes PA, comma, for all x, if px then qx, entails QA. That's a little more surveyable. Okay, so notice that with the exceptions of non-contradiction and cut, all the rules of this system build more complex statements out of simpler statements. For instance, Rule 2, assertion strengthening, lets us go from A to A and D, or D and A. Rule 8, negation denial, lets us go from assertion of A to denial of not A. Each rule of the system, with the exceptions of non-contradiction and cut, builds one new statement, with one new logical connective that wasn't there in the premises of the rule. So I'm going to start working backwards towards the completion of the proof by finding one or more valid sequence which let us derive the conclusion in one step, applying one rule of the system. Because of what the rules do, our objective is to find premises which let us build the outermost logical connective of one of the statements in the conclusion. In this case, we have only one option. We must attempt to build the for all quantifier in the statement for all x, if px then qx. This is the only statement in the conclusion sequent that has any logical connectives to build. So we know that the rule we need to employ is one of the universal quantifier rules because of that. And specifically, it must be whichever of the two rules can be applied to produce assertion, since the statement we're trying to build, for all x, if px then qx, is an assertion in the context of this sequent. Therefore, the rule we need to employ is the rule of counterexample. The rule of counterexample reads as follows. Suppose a1 through an, comma, b with x to t, entails c1 through cn is a valid sequent. Then, a1 through an, comma, for all xb, entails c1 through cn is a valid sequent. So this tells us that the second to last step in the proof should be to derive a sequent of the form a1 through an, comma, b with x to t, entails c1 through cn, which the rule of counterexample will turn into the desired conclusion sequent, namely, pa, comma, for all x, if px then qx, entails qa. So let's find that by matching the conclusion sequent against the form of the conclusion of the rule of counterexample. The form of the conclusion of the rule of counterexample is a1 through an, comma, for all xb, entails c1 through cn. The desired conclusion instantiates this form as follows. A1 through an is equal to pa. X is equal to x. And you can't hear it in the audio, but in this equation, x equals x, this is the metavariable x being instantiated to the variable x. Okay, so then, right, the metavariable b is equal to or instantiated to if px then qx. And c1 through cn is equal or instantiated to qa. So substituting these variables into the form of the premise of the rule of counterexample, we can say that our premise should be of the form PA, comma, if PT then QT entails QA for some object term T. T is the only variable that's in the premise form of the rule of counterexample and not in the conclusion form. And we need to pick a value for T. A sensible guess would be to pick T equal to A. As we will now see, this choice works out and lets us complete the proof. So the final step of the proof we are constructing is to invoke the rule of counterexample to go from the validity of PA, comma, if PA then QA entails QA, to the validity of PA, comma, for all x, if PX then QX entails QA. So PA, comma, if PA then QA entails QA is indeed a valid sequent, as some reflection should show. So in order to complete our proof, we have to prove that it is a valid sequent. We will do this by continuing to work backwards, now trying to find a step that will let us arrive at PA, comma, if PA then QA entails QA. Our goal in this step should be to build one of the logical connectives in our goal sequence. And there is only one choice. We need to build the if-then of the statement if PA then QA. This tells us that we need to use one of the conditional rules, whichever one lets us build an assertion, since if PA then QA is an assertion in our goal sequence. Thus we need to use Rule 6, the rule of conditional assertion. The rule of conditional assertion reads as follows. Suppose A1 through AN entails B, comma, C1 through CM is a valid sequent, and D1 through DK, comma, E entails F1 through FJ is a valid sequent. Then A1 through AN, comma, D1 through DK, comma, if B then E entails C1 through CM, comma, F1 through FJ is a valid sequent. So we can match our goal sequent against the form of the conclusion sequent as follows. A1 through AN, comma, D1 through DK is instantiated to PA. B is instantiated to PA. E is instantiated to QA, and C1 through CM, comma, F1 through FJ are instantiated to QA. And we need to produce two premise sequence, which the rule of conditional assertion will turn into our goal sequence. One of them will contain the assertions A1 through AN and the denials C1 through CN. The other will contain the assertions D1 through DK and the denials F1 through FJ. In this case, we know that the combined sequence of assertions A1 through AN, comma, D1 through DK is equal or instantiated to the one-element sequence containing just PA. So PA goes into either the A sequence or the D sequence, and it's the only thing in whichever sequence it goes into, and the other sequence is empty, right? But we need to decide which sequence PA goes into. And similarly, QA goes into either the C sequence or the F sequence, but we need to decide which. So let's set aside that issue for the moment and state what we know about the forms our premises need to have. We are settled that B equals PA and E equals QA, so we can write our needed premises this way. A1 through AN entails PA, comma, C1 through CM. D1 through DK, comma, QA entails F1 through FJ. So should PA go into the A sequence or the D sequence? And should QA go into the C sequence or the F sequence? If we put PA in the A sequence and QA in the F sequence, then both our premises become instances of the rule of non-contradiction. PA entails PA, and QA entails QA. That's what we get if we do it that way. So that is what we should do, because we end up with two instances of the rule of non-contradiction. So we end up with valid sequences, and we've reached the beginning of our proof. Let's now write out the steps in forwards order instead of backwards order. So 1, PA entails PA is valid by the law of non-contradiction. 2, QA entails QA is valid by the law of non-contradiction. 3, PA, if PA then QA entails QA is valid by the law of conditional assertion and steps 1 and 2. And PA, for all x, if PA then QA entails QA is valid by the law of counterexample and step 3. So let's now write the finished version of the proof by substituting back the original English terms. P stands for is a man, Q stands for is mortal, and A stands for Socrates. This gives us the following proof. 1. Socrates is a man entails Socrates is a man is valid by the law of non-contradiction. 2. Socrates is mortal entails Socrates is mortal is valid by the law of non-contradiction. 3. Socrates is a man, if Socrates is a man then Socrates is mortal entails Socrates is mortal is valid by the law of conditional assertion and steps 1 and 2. 4. Socrates is a man, for all x, if x is a man then x is mortal entails Socrates is mortal is valid by the law of counterexample and step 3. To sum up, the classic argument we have analyzed is valid according to classical logic. Given that Socrates is a man and all men are mortal, it follows that Socrates is mortal. It is incoherent, according to classical logic, to assert that Socrates is a man and all men are mortal, while denying that Socrates is mortal. So the basic proof construction techniques that I have introduced in the context of this argument can be applied to construct arbitrarily complex proofs of the validity of first-order logic sequence. To go deeper into this topic, I refer you to the exercises. To do exercises. That completes my introduction of how to use the rules of classical first-order logic. We can use the rules of logic to establish that sets of assertions and denials are incoherent. The rules of classical logic generate an infinite set of valid sequence, which can describe what sets of assertions and denials are incoherent according to classical logic. So we entered our discussion of classical logic wanting to discover what rules of logical inference are valid. Rules of logical inference let us go from premises that are warranted assertable in a given context to conclusions that are also warranted assertable in the context. We ended up with something slightly different. We got a system of rules telling us what sets of assertions and denials are incoherent. Let's see how we can get back to the topic of rules of logical inference. A rule of logical inference can also be called an argument form. For our purposes, we can equate rules of inference or argument forms with single conclusion sequence possibly containing metavariables. Recall that the result of instantiating the metavariables in an argument form is called a case of the argument form. And recall that I call an argument form valid for a given person when it lacks counterexamples for that person. A counterexample to an argument form for a given person is a hypothetical or real truth-seeking debate context and a case of the argument form where they consider the premises warranted assertable and don't consider the conclusion warranted assertable. Recall also that I call an argument form simply valid if it is valid for people in general. We can call an argument form valid according to classical logic when every instance of the argument form is valid as a sequent, according to the rules of classical logic. Empirically, my psychological notion of validity coincides well, but not perfectly, with the classical logic notion of validity for most people, and the more concrete the problem domain is, the more this tends to be so. In other words, especially in concrete problem domains, it tends to be the case that an argument form is valid for people in general, if and only if all instances of that argument form are valid according to the rules of classical logic. However, there are definite counterexamples to this tendency. Here is one reason one might doubt the closeness of the connection I have stated between the psychological and classical logic notions of validity. One might ask, if it is incoherent to deny a conclusion in a given context, does it follow that it is warranted to assert the conclusion in that context? When a sequent is valid according to classical logic tells us it is incoherent to deny the conclusion in contexts where the premises are held true. When an argument form is valid in the psychological sense, people consider the conclusion warranted assertable in contexts where the premises are held true and thus warranted assertable. So then, if it's incoherent to deny a statement in a given context, given premises that are held true in that context, then is it warranted to assert it? Not always. For example, if the premises that are held true in the context are incoherent, then any additional assertions or denials will be incoherent with the context, because adding more to an incoherent position gives you an incoherent position. Let us then restrict our attention to contexts where the premises held true in the context are, taken together, coherent, i.e., not incoherent according to classical logic. In such contexts, if a statement is incoherent to deny, is it warranted to assert it? Perhaps not, as it might be incoherent to deny the statement, and yet there might be a social taboo/norm of some kind, prohibiting one from asserting it. Let's set aside this possibility as well. Are there any other reasonable significant ways that a statement can be incoherent to deny, and yet not warranted to assert? Yes, there are. Suppose I have a position that is not incoherent according to classical logic. Suppose my position makes it incoherent for me to deny P, and that I just learned this. Suppose P is such a shocking, implausible statement to me that I think it's probably false. I might not consider it warranted for me to assert P, because I might think that the fact that my position makes it incoherent for me to deny P means that there is something wrong in my position. As such, I might consider it unwarranted for me to assert P, but incumbent upon me to reevaluate the assertions and denials in my position. Okay, so a sequent A1 through AN entails B states that it is incoherent to assert A1 through AN and deny B. Even if somebody accepts all the rules of classical logic as applied to this case, and if they believe all of A1 through AN, the validity of such a sequent cannot compel them to accept B as true, as they always have the option of rejecting more of A1 through AN, rejecting one or more of A1 through AN, instead of accepting B. This reflects a broader truth about logical arguments in general. Logical arguments always proceed from premises to conclusions, but they never compel the reader to accept their conclusions. Logical arguments always cut two ways. They can compel the reader either to accept their conclusions or to reject some of their premises. Logic is able to tell us that certain positions are incoherent. This is about all it can do. It can't tell us which of the many logically coherent sets of statements we should believe, disbelieve, assert, deny, hold to be true in a given context, hold to be false in a given context, etc. I started out this section by presenting a one-directional notion of the rules of logical inference, according to which rules of logical inference let us pass from true, warranted assertable statements to other true, warranted assertable statements. Our inquiry has shown us that this is an incomplete picture of how logic works. Every person who accepts the rules of logic and reads a logical argument has two options: to accept the conclusion, or to reject one or more of the premises. In real debates, logic is not necessarily used simply to pass from truth to truth. Instead, logic constrains humans to bounce about as they will, in the space of logically coherent positions. In practice, of course, humans often find themselves in logically incoherent positions. It may take them a long time to notice that, and they may never notice or never care. Okay, so suppose that A1 through AN entails B is a valid sequent according to classical logic. Suppose that I accept the rules of classical logic. Suppose A1 through AN is a coherent set of assertions, or in other words, that it is not incoherent according to classical logic. Or in other words, that A1 through AN entails nothing, right, an empty sequence of statements, is not a valid sequent. Okay, so suppose that I accept all of A1 through AN as true, and that for the purposes of this question, I am not going to back down from any of these premises, i.e. A1 through AN. And suppose that in the context under question, I am not prohibited from asserting B by any social taboos or norms. So given the suppositions I've just stated, it's incoherent for me to deny B, right? Is it therefore warranted for me to assert B? Okay, so now finally the answer seems to me to be yes. At least, I am unaware of any further qualifiers that need to be added. However, it does not follow from the rules I have already stated about classical logic that in these circumstances it is warranted for me to assert B. Rather, this seems to be an additional principle about classical logic. So here is Rule 16 of my presentation of classical logic, which is the law of inference. So suppose A1 through AN entails B is a valid sequent. Suppose A1 through AN is coherent according to classical logic. And suppose it is warranted to assert A1 through AN in a given context. Then, either it is warranted to assert B in the given context, or re-examination of the warrant to assert A, to assert A1 through AN, is warranted. This is a restatement in the form of a rule of the question posed 3 paragraphs above. So I removed the qualifier that asserting B is not prohibited by any social taboos or norms. Any context where this would be a blocker to assertion, despite the other conditions holding, is not a context where the rules of classical logic hold sway. So now I'm totally finished describing the rules of classical logic until we get to the topic of paradoxes, where I will introduce one more rule for dealing with paradoxes, and that's in the future section titled Paradoxes. Okay, so along the way through stating the rules of classical logic and describing how to use them, we have accumulated a truly impressive series of qualifiers and disclaimers about the rules of classical logic. And I'm just going to restate the law of inference for you, which summarizes this whole discussion. Suppose A1 through AN entails B is a valid sequent. Suppose A1 through AN is coherent according to classical logic. Suppose it is warranted to assert A1 through AN in a given context. Then, either it is warranted to assert B in the given context, or re-examination of the warrant to assert A1 through AN is warranted. Okay, so we have not yet scratched the surface of the debates about what specific rules of logic are correct. Classical logic represents the dominant point of view about what rules of logic are correct, but there are competing sets of rules for logic. So-called non-classical logics are intended to address perceived deficiencies of classical logic, generally speaking. So in almost every case, non-classical logics are sets of rules which are weaker than the rules of classical logic, in the sense that the sets of assertions and denials that a non-classical logic counts as incoherent is typically a strict subset of the set of assertions and denials that classical logic counts as incoherent. Okay, how correct are the rules of classical logic? Given the complexity of the rules themselves and the trouble that has been involved in describing them, this may appear to be a difficult question. It is. So let's get started. I will start by presenting the best argument I can, to the effect that the rules of classical logic are correct. Specifically, I will argue that the rules of classical logic correctly capture the notion of validity in the sense that an argument form is valid if and only if it is valid according to classical logic,